Hello everyone, and welcome to Rotational Kinematics. So today we're going to be looking at rotational kinematics. So what is basically rotation? Rotation is simply defined as when a rigid object moves around on circular paths around an axis of rotation. So in other words, it is basically spinning around, so the object is spinning around a central point, a central location. So the first thing you have to know is what is basically the angular displacement. In class, we've seen multiple forms of displacement, but in this case, now it's going to be angular. So the difference for this, it is going to be, since the object is rotating, as you guys can see with the CD spinning, there is going to be a change now in degrees. So the problem now becomes the following. We need to know directionality because why? Displacement is a vector quantity. So what I want you to know is this, that angular displacement is positive if it's counterclockwise and negative if it is clockwise. Okay? So the units though, we cannot use degrees. We have to use radians. And the conversion, it is symbolized by rad, R-A-D. The conversion is very, very simple. Okay? So the conversion is 2 pi rad equals 360 degrees. Some of you may have even learned this in math, and that is pretty much the connotation that we're going to be using. I like to use 2 pi rad equals 360 degrees and not pi rad equals 180 because 360 is simply one rotation. So if the question is talking about a revolution, you can simply assume that is 360 degrees. So theta in radians, it is basically the ratio of the arc length, which is symbolized by S, as you guys can see, divided by the radius, the distance, of course, from that central point by which it is spinning. So, in order to convert degrees into radians, you simply have to multiply the number of degrees that they give you, okay, by 2 pi rad and divide it by 360. Let's do our first problem. Okay, we have synchronous satellites that are put into orbit, and the radius is given to us as 4.23 times 10 to the 7 meters. And now they're telling us that the angular separation of the two satellites is 2 degrees. And they're asking us to find the arc length that basically separates them. So let's go right over here to our trusty sketch pad. Okay, let's open it up and let's check this out. So they gave us, so they gave us the radius. It is simply 4.2 times 10 to the 7th meters, and the theta, the degree separation, that is of course 2 degrees. And here we arrive to our first problem. Okay, they're giving it to us in degrees. So what do we basically say? We basically say that we need it in radians. Okay, so we got to convert degrees now into radians. So this is how we do this. So we have 2 degrees, as you guys can see over here, times, and what do we basically say? You're going to multiply it by the conversion factor. In this case, it's going to be 2 pi rad divided by 360 degrees. So the units, numerator, denominator, they cancel, degrees cancel, and we are left with rad. So if you take 2 times 2, which is 4, times 3.14, which is 12, divided by 360, we simply see that the angular displacement now of 2 degrees, that is going to be 0.0349 rad. So we took the 2 degrees, as you guys can see over here, and we converted it now into rad. These units over here that we want and like. Now it becomes an easy solve because why? We can now put it into our regular equation that we know. So theta equals, we said, S, which is the arc length divided by radius. So we cross multiply because we're trying to find this S over here that is called the arc length. In other words, it simply is the circumference. That's all it is. It's a section of the circumference. R, of course, is radius. Okay, and of course theta is the degrees in radians. So when we cross multiply, we see that we have S, what we're trying to find, equals theta times R. Okay, so theta, we're not going to use, of course, degrees. We're going to use this over here that we just got, and that's going to be 0.0349 radians okay? And we're going to multiply by the r, the radius that they simply gave us. I don't have any space, so forgive me. I'm going to write it at the bottom. So it is 4.2 times 10 to the 7th meters. And when we multiply these two, we should get an arc length of 1.48 times 10 to the 6th meters. Okay, so that, of course, ladies and gentlemen, is the answer. And we saw that it is 1.48 times 10 to the 6th. And I'm pretty sure if we go back to our PowerPoint and we go to the next slide, it's going to be approximately that. There we go, 1.48 times 10 to the 6 meters. And of course, and next to it is converted into miles. Okay, so with that said, let's just erase this very, very quickly. So let's click new, don't save, and let's continue on with our presentation. So we just said that the change in angle of displacement, that is theta final minus theta initial. Okay, so now so if that's displacement, how do we actually describe the rate, which is of course the change of displacement, the rate of change of displacement, that is velocity. So just like we did with linear kinematics, we basically said that angular velocity is the change of angular displacement divided by the elapsed time. So it's delta theta over delta t. So now, just like velocity, which was in linear terms, which was meters per second, now, because we're talking about the angular displacement now, it's going to be rad per second. So it's not going to be meters per second, but rather rad per second. And again, the same rules count if you're given now something in meters or degrees, you would actually have to convert it into radians. So here we go. Let's try to solve a first one. So we have a gymnast on a high bar swings through 2 revolutions at a time of 1.90 seconds. Find the average angular velocity of the gymnast. So first of all, let's look at the picture very quickly. So look at the direction of the arrow. Is that clockwise or is that counterclockwise? That is clockwise. And if you remember correctly, clockwise is always given by negative. So let's go into our trusty sketchbook and let's see. So we said angular velocity is the change of angular displacement divided by change of time. Okay, so here's the thing. They gave us, okay, 2 revolutions. Okay, so REV, 2 revolutions. So as obviously we got to convert that now into radians. So what do? We multiply it again by 2 pi rad, and that's why I like 2 pi rad, divided by now instead of 360, which is what we regularly do, we now divide it by 1 revolution. So revolutions drop out, so we're left with 2 times 2 pi rad. So that is, of course, going to give us negative, because we said it's going to be it's clockwise. So it's going to be negative 12.6, and it's going to be radians. So we just figured out the change in angular displacement. And the change of time, of course, they gave it to us. So the problem said, so it's going to be delta theta divided by delta t. So it's going to be negative 12.6 rad, that's what we just calculated, divided by 1.9 seconds. And if we divide these two, that is going to be negative 6.63, and that's going to be radians per second. Now notice how it's very similar to linear, but instead of meters per second, now it is going to be radians per second. So if I toggle back into our presentation, and I go a little bit down, I can see, yep, that's exactly what we got, negative 6.63 radians per second. Okay, so let's erase this, and obviously it makes sense once we speak about angular displacement, angular velocity, the next thing that we're going to talk about is going to be angular acceleration. It just simply makes sense. So let's look at now angular acceleration. So what is angular acceleration? It's symbolized very similar to the linear acceleration that we have, but now it's going to be the change in angular velocity divided by the change of time, so the change of elapsed time. So if you remember correctly, acceleration was what? Meters per second squared. In this case, angular acceleration is going to be radians per second squared. So going down, we see. Let's do the following problem. As seen from the front of the engine, the fan blades are rotating with an angular speed of negative 110 radians per second. As the plane takes off, the angular velocity, so that's the final velocity, is negative 330 rad per second in a time of 14 seconds. And they're asking us to find the angular acceleration. Okay, so the negative 110, obviously negative, that means that it's going to be what? Clockwise. And you can see from the diagram over there, the fan blade inside the jet is rotating clockwise, so that's why it's negative. So that is velocity initial, and velocity final is going to be, angular velocity final is going to be negative 330 rad per second in a time of 14 seconds. So we go back to our trusty sketchbook and we see. So angular acceleration is given by this little symbol alpha. It is going to be now omega angular velocity final minus angular velocity initial, sorry, that's omega, divided by delta t. So now we just simply plug the values in. So final velocity was negative 110 rad per second, those were good units, minus now the initial, which was negative 330 rad per second. And we divide this now by the time, which is 14, okay? I may have actually, by accident, I switched the two values. So it is actually negative 330 rad per second minus 110. That's initial and that's final. Sorry about that. And we divide this now by the seconds, which is 14 seconds. And if we do this, we clearly see that that's going to be negative times negative, that's going to be positive. So 110, that's going to be 220 divided by 14. So that's going to be negative 16 rad per second squared. And notice how similar the units are in terms of linear. Instead of meters per second squared, it's now rad per second squared. Thank you, everyone.